Okay, so we are going to start a discussion about the harmonic oscillator. So this is the beginning of the section 2.3 of Griffith's book, third edition. And at this point, we are just going to start with a discussion. We're just going to talk about why the harmonic oscillator, so the harmonic oscillator is such an important problem. And in the next video, then we will start talking about more details about the quantum harmonic oscillator and how to solve Schrödinger's time-independent equation. Okay, so for the moment, we'll just start with a very general discussion. And for that, we're going to start talking about the classical harmonic oscillator. When you usually, the way that we first get exposed to the classical harmonic oscillator is thinking about a spring. So here we have a spring at its natural length. Let me try to make this drawing a little better. So at its natural length, and it's there at rest. But then if we, for example, stretch, and so if we stretch this spring, so now it is at this new position A, and so when we do that, this system gains potential energy. And so at this point here, it has maximal potential energy. As we let it go, the motion starts, and then this object will then be moving, in our case here, to the left. So we'll be gaining speed, it will be gaining kinetic energy, and it will be losing potential energy. Once it passes through that point, that natural length of the spring, it will pass with the maximum speed and will keep going until it gets maximally compressed at this position now minus A. At this point, again, it has maximal kinetic energy, but the speed at this point will become zero. And it will then, at this point, start moving to the right. And it will go back and forth in this motion. If we don't have friction, it will be going back and forth forever. And we learned that this is an example of a harmonic oscillator. What is the force involved here? Well, it's what we call a restoring force. So it has this negative sign because it's always opposite to what we are doing. Now, if we stretched, then it wants to compress. Once it is compressed, then it wants to stretch. And so it's always against. So that's therefore the minus sign, therefore the restoring name. Then there is a K, which is the spring constant, and the displacement, right? So this is the force associated with this motion. But after this spring, that's usually our beginning, the introduction to the harmonic oscillator, we learn other systems that also have the same kind of motion. For example, the pendulum, right? If this angle here is not too large, we can describe this back and forth motion, without friction again, as a harmonic oscillator. Another example is a circuit, is the LC circuit, right? What is the LC circuit? You have a capacitor, inductor. When it's maximally charged, you have big potential energy. As it's discharging, you have the current going through the circuit. So you go again in this back and forth motion. Very good. Let's talk a little bit more about this equation that we wrote here, right? We can write this equation using what the force is, mass acceleration. So mass acceleration equals to minus kx. So we end up with this equation, with this second order equation, which we know very well how to solve. Now, we even already discussed that. How do we solve this equation? Well, sinusoidal functions. Now, if you, what happens here? We do the derivative twice and we recover the x. with a minus sign. Well, that's a sinusoidal function. So the solution here is sine of that k over m. So, sorry, t, no, it's the derivative is in t in time, with some constant in front or a cosine. And here there is a square root, because we do the derivative twice. So after doing it twice, we get k over m. Therefore, we have a square root here. And here we have, right? And again, since this derivative is done twice, we are going to get that minus sign. So you see that this is indeed the solution. So what we have here is this sinusoidal motion. And since here we have a frequency, right? It's the frequency of this motion. We often also write that as omega, where omega is the square root of k over m, right? Very good. Let's keep this here, and now let's talk about this force, right? So if this force, this restoring force is written like this, what is the potential energy associated with this motion? Well, we know that force is minus the derivative of the potential energy. So if that force is minus kx, we know that the potential energy is 1/2 of kx squared, right? You do the derivative and we are going to get that. So either we write like this, or if you want, using the frequency that we just talked about, we can say that this potential energy is, let me write this here, K is m omega squared, correct, from this equation. So then we can say that the potential energy is 1/2 of m omega squared x squared. So this is the potential associated with the harmonic oscillator, with this motion that we call the harmonic oscillator. Why is this problem? Why is this harmonic oscillator so important? Because as you see, there are many physical systems, real physical systems described realizing this kind of motion. And, what we are going to be doing is we are going to study the quantum version of that. So we talked about a circuit here, a classical circuit, but if it becomes microscopic, we'll have a quantum circuit that can again be described by this harmonic oscillator, but a quantum harmonic oscillator. Another example, like vibration of molecules, can also be described by a quantum harmonic oscillator. So you see how many different problems have this topic of harmonic oscillator in common. So why are there so many systems that can be described by this uh, um, potential energy? Well, the idea is the following. Even if the problem is not exactly described by that, as is explained in your book, suppose you have a certain general potential for a complicated problem, okay? And here, around this minimum, around this minimum, we can approximate this complicated potential around this minimum. We can approximate it with this parabola. With parabola means this x squared. How do we know that? Well, let's suppose you have a function for your potential, your potential energy. And let's do an expansion for this potential and around that minimum point that we identified. So what do we get? Well, Taylor expansion. Okay, so this is what we are doing here. So the Taylor expansion around that minimum. So first term is the potential right at that point. Well, this is just a constant. Then we come the derivative of that function and we put it right at that point with x minus x0. But remember, we said that this is a local minimum. So if this is a local minimum, this is 0, right? Okay, and what is the next term then? The next term is going to be the second derivative. At that point, there is a half here and x minus x naught squared. So you see that the first dominant term in this expansion is the x squared that we are talking about. So there are many problems that can be approximated by this harmonic oscillator. So that is why it's so important. Now, what we are going to be studying, as we said, is the quantum. We put it in orange, now the quantum harmonic oscillator. And what does that mean? Well, it means that we can write our Hamiltonian. Hamiltonian involves the kinetic energy, it involves the potential energy. And what is the potential energy? I'm going to write with this form here. So the potential energy, 1/2 of m omega squared x squared. And what happens when we are dealing with a quantum harmonic oscillator? Well, these are operators, correct? And what we are going to do? Well, this is our Hamiltonian. We need to now solve the time-independent Schrödinger's equation. That's what we need to solve. Okay, and this is going to be the discussion now for the next video.